Hey everyone, a huge welcome to all of Mr. T's students and, of course, all the followers. If you're coming over from TikTok or YouTube, you already know what we're about to do. Today, we are diving deep into one of those questions. You know the ones, the kind that can really make or break your paper. Yep, we are cracking question 5.
So you're in an exam, you turn the page, and you see this, a monster question clocking in at 17 marks. It's got calculations, it's got theory, it's got graphs, it's got everything. And it's totally normal to feel your heart sink a little bit. But you know what? That feeling, it stops right here, right now.
Because you are absolutely in the right place. In this explainer, we're going to break it down piece by piece. Our goal isn't just to get through it, it's to completely master it. Seriously, by the end of this, you're going to look at a question like this with total confidence, knowing exactly how to lock in every single one of those 17 marks. Okay, let's get into it. Before we even think about touching a calculator for that big 6-mark calculation, we've got to lay the groundwork. You know, the theory questions are where you find the easy marks, and they really set the stage for everything that comes next.
First up, question 5.11. It's asking for a simple definition. What is the reaction rate? Easy. It's the change in concentration of your reactants or products per unit time. The magic words there are per unit time. And hey, the marking guide is pretty cool about it. It'll also accept changes in amount, moles, or mass. Nailing this definition, that's a quick 2 marks in the bag.
So here we have a classic Maxwell-Boltzmann curve, which is really just a fancy way of showing the energy of all the particles in a system. The question is, what change turns curve X into curve Y? Well, look at curve Y. See how it's kind of lower, flatter, and stretched out to the right? That shift to the right means the average kinetic energy is higher. And what gives particles more energy? An increase in temperature. It's that simple. You get 1 mark for saying temperature increase and another for explaining why.
All right, here we go. The main event, the big one, the 6-mark calculation that can really separate the pack. But trust me on this, it is not as scary as it looks. All we need is a clear strategy, a roadmap to follow, and we'll walk right through it.
And here it is, our roadmap to those 6 marks. The whole strategy is about working backwards. We're going to use what they tell us about the product, the hydrogen gas, to figure out how much of the reactant, the aluminum, actually got used up. Let's just take it one step at a time.
Okay, let's knock out the first 2 steps. The question tells us the rate of hydrogen formation is 0.033 cubic decimeters per minute. This goes on for 5 minutes. So, simple multiplication gives us the total volume produced, 0.165 cubic decimeters. Great. But volume isn't super useful in chemistry. We need moles. So we use the molar gas volume, Vm, which is just a constant they give you. Volume divided by Vm, and that gives us our moles of gas.
And that comes out to 0.0067 moles of hydrogen gas. This number right here, this is the golden key. It's going to unlock the whole rest of the problem for us. We just turned a rate into a real chemical quantity.
Now listen up, because this next step is where marks are so easily lost. The mole ratio. This is non-negotiable. You have to go back to the balanced equation. It's your source of truth. It tells us that for every 3 moles of hydrogen gas we make, we must have used up 2 moles of aluminum. This 2-to-3 ratio is the bridge that connects what we made back to what we started with.
So we use that 2-to-3 ratio to figure out the moles of aluminum that reacted. Then it's pretty straightforward. We turn those moles into mass using aluminum's molar mass right off the periodic table. And now for the final step, and please watch out for this, it is a classic exam trap. The question asks for the remaining mass, so we have to subtract the mass we used from the 0.5 grams we started with.
And that leaves us with our final answer, 0.38 grams. We started with 0.5, the reaction chewed through 0.12, and this is what's left. Boom! 6 marks, secured.
Fantastic. The heavy lifting with the calculator is done. But we are not finished yet. Now it's time to lock in those other marks by explaining the theory and interpreting the graphs. This is all about showing you understand the why behind all the numbers.
Next up, we use collision theory to explain why the reaction slows down. Just think of it like telling a logical story. Step 1, the aluminum strip reacts, so it physically gets smaller. Step 2, a smaller strip means less surface area is exposed to the acid. Step 3, fewer exposed particles means you get fewer effective collisions every second. And what's the definition of a slower reaction rate? Fewer effective collisions per second. Each point in that story is a mark.
Okay, let's compare experiments. In experiment 2, they double the concentration of the acid. Well, more acid particles packed into the same space means more frequent collisions, right? So the initial reaction is going to be way faster. But, and this is the critical part, the final amount of product you make is exactly the same. Why? Because the aluminum is the limiting reactant. It doesn't matter if you have an ocean of acid. Once that 0.5 grams of aluminum is gone, the party's over.
And this leads us perfectly into the graph question. For experiment 2, you draw a curve. Let's call it curve B, that's much steeper at the start than curve A, but it levels off at the exact same final volume. Faster rate, same yield. And you know what? The exact same logic applies to question 5.1.5. If we used powdered aluminum instead of a strip, the rate would be way faster, but the final volume of gas produced would be, yup, you guessed it, exactly the same.
And that's it. We have cracked every single part of question 5. But before we wrap this up, let's just lock in the key strategies that are going to help you turn this knowledge into maximum marks on your real exam paper. So, here are the big takeaways. Number 1, always write down your formula before you start plugging in numbers. It gets you marks. 2, the mole ratio is everything. Double check it. 3, remember, a faster rate does not mean more product. And finally, please read the question carefully. It asks for remaining mass. That one little word is the difference between getting the question right or wrong.
And really, it all comes back to something Mr. Chi always says. Clarity is the key to confidence. My hope is that by making every single step of this question crystal clear, you now feel a whole lot more confident about tackling it on your own.
If this breakdown helped things click for you, and you want more clear, confidence-boosting science explainers just like this one, you have to make sure you're following Mr. Chi on TikTok and subscribe to his channel on YouTube. That's the spot to find all the content that'll help you ace your exams.
Okay, I'll leave you with one final little thought to chew on. We've talked about concentration, we've talked about surface area. Thinking back to that Maxwell-Boltzmann curve we saw earlier, what's one other thing you could change in this experiment to get an even faster reaction, but without changing the final amount of product? Give it some thought. Thanks for watching, everyone.